Welcome back. So we were talking about protection last time, and we started out by talking about multiplexing of memory resources. And we kind of identified at least 3 goals, maybe, of trying to multiplex memory resources in particular. So one of them was controlling the overlap specifically so that when we don't want to reuse memory, we don't, and when we want 2 threads or processes to share memory, they can. And that was one sort of desirable aspect. Another was this notion of translation, which is pretty useful as a way of basically allowing different processes to not have to know where they are in physical memory. By translating, we basically hide that level of detail from them, giving us much more of a virtual machine view of the world. And then finally, protection is got kind of 2 aspects to it. One of it, which we introduced on the first day, I believe, was this notion that 2 processes are protected from one another by making sure that their memory never overlaps. That's kind of a boring type of protection. More interesting comes into play like certain segments are only read-only, or certain segments are marked as invalid until you try to touch them, then the operating system gets at control and does something interesting. So we'll talk about all sorts of uses of protection as we get on a little later. But so these were sort of 3 goals. And this was kind of our iconic view of the translation and how it prevents overlap. So basically, this is the address space of one process. This is the address space of another. Those actual reads and writes in the virtual space gets translated into physical space. And depending on how we set up these little blue bubble translations, we can get protection, we can get controlled overlap, we can get translation. So, why are we not done with this picture? Well, in some sense, these little blue bubbles are a mystery, right? And that was what we started on last time as to what exactly that means. And this was the simplest form of segmented protection here that we talked about, in which a virtual address is taken out of the CPU and it's added to a base value, which gives us a physical address. And by the way, we also check a limit to make sure we're not bigger than some limit. So notice, by the way, that this particular scheme, somebody explain to me why this particular scheme translates. What's the translation aspect of this simple scheme? Yeah. Yeah, so we add the base address to the virtual address. We're translating so that as a result, the process that's running basically gets to think it's got address 0 even though it doesn't. Okay, does everybody see that? What's the protection aspect here? Anything below the base is protected. That's certainly true, assuming that virtual addresses can't be negative. Okay, what else? Yeah. So anything above the limit's protected. Good. And then last but not least, what else? Yeah.
Only you have access to memory between the bases.
Yeah, so there's a subtle little protection thing. Assuming I don't screw up in my assignment of limit and base, basically when somebody else has their translation loaded, then they're not going to have access to my memory. Okay, so that last one may have been a little subtle, but basically it gives the program illusion that it's running in its own little space. Is everybody clear on this? Are there any questions? Interesting subtleties here. What happens if there's an interrupt and we want to run some routine in the kernel? Yeah, so somehow our interrupt hardware has to update limit and base automatically for us, because if we just interrupted and tried to start executing the kernel, we couldn't have access to it, right? So just drawing a diagram like this, there's clearly a bit of overhead that has to be handled for things like interrupts, okay? Good. Any questions on this? This is what we would call the simplest form of segmentation, all right? This was actually in the Cray 1, so that's a long time ago, 1964. I'm sure you all remember that. The downside of this is it's very simple, okay? So one of the biggest problems was fragmentation that we mentioned, which basically the memory that we're using, the physical DRAM, has to be allocated in some way to deal with all the segments, okay? So for instance, you know, we start out allocating it this way. We put OS here, process 2, process 5, 6, whatever. And then process 2 finishes. That leaves a big hole, which maybe we can sort of fill with process 9, which we can sort of fill with process 10. But basically, we get this fragmentation problem. And essentially, if you run the OS long enough, you're going to get into a scenario where you got a bunch of little tiny holes. And the best thing you have here, our best option so far is, I don't know, copying some process's segment somewhere else in memory and updating its base and limit registers. So that's pretty expensive, right? And it all happens because fragmentation is an issue here. And the other thing is we don't really have any dynamic growth options here. I guess, for instance, if we had this memory map, we could have process 9. Maybe we could grow space down by adjusting its base down. Or if we had something, maybe the OS can get space by growing its limit up. But we're pretty restricted in what the OS can do for memory allocation. So this seems good. The hardware is really simple, but it's just too simple. And basically can't have stacks and heaps that are easily allocated. And it's also, you know, if you only have a base and a limit register, you can't really share very easily. Probably your only option for sharing is somehow arrange so that these two overlap each other, so that the upper limit of one overlaps the lower limit of the other, and that's just not flexible at all. In fact, so inflexible that people just wouldn't do that. Okay? So we've got our work cut out for us. We want to somehow do something better here. Okay? Now, I'm about ready to move on. So were there any questions on what we did last time before we delve forward? Yeah, you can also share via external resources like disk. Yeah, and in fact, that's exactly what you'd have to do here. Okay. So today we're going to go through a boatload of address translation schemes, and then we're going to go back and talk about dual mode with the difference between kernel and user, and we'll sort of throw in a little bit about the x86 rings in here, and go forward. Okay. So if we want to have more flexible segmentation, that's what I would call inflexible segmentation, we'd like to do something more like this, where the logical space of a process has a whole bunch of different segments, like a subroutine segment for some particular subroutine we care about. Maybe there's a stack segment. Maybe there's a main program segment. So we could imagine having these chunks of memory, and they're sort of floating in space here because I'm not assigning any linear relationship amongst them, just that within each of them there's some continuous chunk. And we could imagine somehow taking this chunk space, I've just sort of put some colors here, and feeding it into physical memory space this way, so that this particular segment 1 is actually there, and segment 4 is actually there, and 2 and 3, and so on. And what this does for us, by having more than one segment per program, is now suddenly we have a lot more flexibility. So for instance, we could allow segment 2 to have some space above it, so we could actually grow segment 2 maybe for a heap. Okay? Or we could have segment 4 grow downward for a stack. Okay? So just by having more than a single segment, we're suddenly much more flexible in what we can do. Okay, we still have a fragmentation problem. Why is that? Yeah, so basically what you just said there is the sizes of these chunks are different. Okay, so the fundamental issue here is the different sizes. Does everybody see that? Okay, if all chunks were the same size, then we wouldn't really have an issue. But the fact that we might want to have big ones and small ones gives us a problem. Okay, and we'll have to deal with that in a moment. But let's take a look at how we might support this model. So we're going to start with a segment table. And right now, this segment table we'll assume is actually inside the processor. And each entry in the segment table has both a base and a limit. Not entirely surprising. Okay, so each one of our segments, here there were 4 of them, here I'm showing 8, has a base in physical memory and a limit and a valid bit, which kind of says, is that segment even valid at all? Okay, and how do we access this? Well, our virtual address, we now are going to divide up into 2 chunks, a segment number and an offset. And that segment number is basically going to be used directly as an index into the segment table. And that's going to select which base and limit are of interest. Okay? And then we're going to take the offset and add it to the base, and that's going to give us the final physical address that the processor is requesting. So we take the physical address coming out of the processor, we look up the segment, we take its base, we add it to the offset, that gives us a physical address. And what we've just done is we've come up with an explicit mechanism for handling this, in which we put an explicit ordering on the segments, and I'll show you that in a moment. Okay? Now, of course, there's some errors we could run into, like, for instance, if the limit for a given segment is exceeded by the offset, then we'd say, okay, that's an error. Okay, and maybe we cause a page fault or something. Well, not a page fault, a segment fault. Okay? And we have as many individual chunks as we have entries in the table. Okay? Now, what's interesting is this is one technique where essentially we take a few bits out of the address and use them to index. The x86 kind of gives you a different technique where the segment register you're using actually comes as part of the instruction. So in this case, we're using the ES segment register, and that defines what the base and limit is. And we use that plus the offset, which is the BX register, to compute a memory address, which AX then uses. Okay? Good. So what are the V's and the N's? Well, this is valid, not valid. Okay? So we could, in some sense, turn off a segment just by marking this as an N. And so we have done that. So there are some segment number combinations here which will reach an invalid. And then potentially at that point, if we tried to access them, we'd get a fault. And I'll talk more about that later. Okay? So does this idea make sense to everybody? Question? Yes?
Wouldn't some of the chunks, for instance, like the code segment, unless it's like a self-mutating program, it would never grow, right? So if you could allocate those in a smart way, like if you know that they're going to grow, then that's kind of right?
So we can certainly use knowledge of our segments, like this fact that maybe the code segment will never grow, to help us. That's true. And so that would, maybe by putting them all together, we avoid some fragmentation. I'll buy that. We would like to actually completely fix fragmentation in a moment. But if you're stuck with this kind of hardware, you might have to do that, yeah. Any other questions? Okay. So in fact, if you look at the x86 architecture, it, of course, supports segments. And what's kind of interesting about it is the x86 is nothing if not legacy. Okay, so if you don't know the story of the x86, it started out as the 8086, which was only produced in the 8088 version originally, which was an 8-bit version of a 16-bit processor. And so a lot of the stuff that was in there was legacy through the 8186, the 8286. Finally, in 8386, you actually had real protection of the form that we might talk about. And so you might ask yourself, well, okay, by 8386, were all these segments still necessary? Well, that's actually an ongoing debate, depending on whether you run this thing in flat or segmented mode. But let's talk about the segments here. What actually happens with the segments, and here's a layout of the segments. We have 14-bit index, which when you use, say, segment CS, that 14-bit index is actually indexed into a table in memory which looks up the base offset of that segment, and then you use the resulting base and offset to add to the offset of, or excuse me, base and limit to add to the offset of the other register you're using, and that gives you an address. So this is pretty complicated. And in fact, notice I'm explicitly not talking about the requester privilege level, which is, notice there are 2 bits there which give you 4 rings, and this is kind kind of how privilege comes into play, because the CS register sort of says what privilege you're running at. So we won't even worry about that. But you can see that the segment scheme here is pretty complex. But potentially you can do a lot with it. So with these 14 bits, it's actually 13 bits plus a table indicator is 14 bits. That's 14 bits worth of different segments that you can actually have access to in theory simultaneously. And each one of those segments can be 32 bits in a simple case, and so it's a lot of possible segments, okay? You can only have 6 of them loaded at once. All right. So x86 is a complicated processor, if you hadn't figured that out yet. Does anybody know what the current instruction count is on the x86? Okay. We have somebody that says in the front maybe it doesn't matter, but does anybody know? Order of magnitude, is it 10 instructions? 100 instructions? 1,000 instructions? Yeah, it's order 1,000 to 10,000 instructions. There's a lot of instructions. Okay? You've heard of complex instruction set computer. That pretty much hits it. All right. So let's take a look back to our more simple segmentation scheme we had before. And first of all, I want you to look at this segment setup here and realize that if we take the top 2 bits as our segment register or our segment ID, we have now split the virtual address space into 4 pieces. Because I'm making this a 16-bit space just to be easy, but if we go from 0 here down to 65,535 or FFFFF 4Fs, what we see is there's actually 4 chunks that represent each segment, because as we're counting from 0, here we're in segment 0, then we go to segment 1, then we go to segment 2, then we go to segment 3. Is everybody with me on that? Okay, who's not clear on that? Go ahead, raise your hand. What's not clear? Now notice, let me do that again. So we start here. The fact that these top 2 bits are being used to say which segment we're in means that as we count from 0, 0, 0, 0 up to FFFF, we're actually, as we count, we fill up the offset, then we overflow, so offset's all 0, and this becomes 0, 1, in which case we go from segment 0 to segment 1 to segment 2 to segment 3. So our actual address format is forcing a format on the way the virtual address space looks. Now, what's interesting is because when we add the segment table into this, we see that segment 0, for instance, has its own base and limit. And so the fact that here's segment 0 is actually going to be here, starting at 4,000 hex in memory, in DRAM, in the physical DRAM, and it has a limit of only 800 hex. So it's a little thin sliver, which means that these addresses here get translated to these addresses there. And once we get up to segment 1, we see that, wow, segment 1 starts at 4,800 base, which is right there. Its limit is 1,400. It's this sliver that size. And so this set of addresses get translated there, and so on. Okay? Now, what happens if we try to access an address here? Okay, I hear segment fault. Somebody tell me why that might be. Well, actually, it gets caught before that. So how do we catch the fact that this doesn't exist? Yeah.
The limit of the associated segment is much smaller than
Yeah. So let's think through this translation. If we're up in here, first of all, when we take our address, the top 2 bits are going to be 0, 0. So we're going to look up our segment ID 0. And we're going to say, well, how far are we? Well, the offset is what we get when we remove the 2 bits. It's going to be up here. And that offset will be bigger than 0x 0800. And therefore, we're going to call that a fault. Okay? So basically, everything in the white chunks here are all segment faults because they're outside of the specified address space. Now, if we wanted to try to find more space for this segment, we could increase the limit. Okay, but notice the problem. Right now, we can't increase the limit because this little pink chunk is jammed up against the blue chunk. So what we'd have to do is we'd actually have to copy this segment somewhere else, and then we'd have more space, and then we could increase the limit and change the base. Okay? This is the simplest translation you could come up with. So let's make sure we're on top of it. Questions? You want to go through an example? Let's do an example. So here's an example. So here's some code. And notice what I've done here is I've put the assembly language off to the side, even though we all know it's actually translated to machine language. And here's the actual addresses. Okay? And let's simulate a bit of the code. We're going to start our program counter at 0x240, which is right here. Is that a virtual or a physical address? How do we know it's a virtual address? It's coming out of the processor. Okay? Therefore, it's a virtual address. Okay? So now we're going to fetch 0x240. So why are we going to fetch that? Well, that's where the next instruction is. Remember, our PC is at 240. Okay, so what's virtual segment 0? Offset 240. Okay, so how do we know that's true? Virtual segment 0. Why do we know that PC 0x240 has a virtual segment number of 0? Yes? Yeah, so remember we're working in this space, so we're taking our 16 bits and we're thinking about those top 2 bits. Okay, so in this, if we think of our 16 bits, that's 4 nibbles, right? And the top hex digit here is 0. So, and the top 2 bits of that 0 are zeros, and therefore our segment is 0. Okay, could you guys all do that sort of translation in your brain? So what's the physical address? Well, virtual segment 0. I could have sworn I actually had our segment ID here. I do. Why is that not coming up? It's a mystery. Let me, oh, that was interesting. All right, that'll help. You'll have to ignore the fact that came in last. Okay, so let's just take a look here. Excuse the fact that this is all up on a slide. So if we fetch 240 hex, what's virtual segment 0? Okay. Well, it's base 4000, limit 800, okay? So that means, since our offset is 240, that's going to be annoying to you guys here. Let's just do this. Oh, can I do this on the fly? Let's see, no animation. I guess I can't do this on the fly because it's Windows 10 or 2010. That's annoying. All right, sorry about that. Okay, so if you take a look, so ignore everything below this. So notice that we're taking virtual segment 0, looking it up in the table. That gives us base 4000. Is everybody with me on that? If we've got base 4000, now physical address is, well, we take the 4000 plus our offset, giving us 4240. Okay? Now, the question is this offset okay? The way we do that is we say the offset's 240, we look it up, the limit's 800, so we're okay. Okay, so this is not going to fault. So our physical address is 4240, which means we actually go to 4240 in the DRAM to get our instruction. And that instruction, okay, what we're going to do there is we're going to basically move. So the fetch instruction's at 4240. Okay, does everybody see that? Okay. So the next thing we're going to do is load what's in A0, okay, which is basically var x. Where's var x? Does everybody see that here? Var x has 4050 in it. So basically, we're going to load 4050 into A0. So 4050 moves into A0, and we're going to add 4 to the PC. Okay, so now, questions on that translation, just that little segment there. Yes, question.
Why is the address for var x virtual as well?
Yeah, everything the processor knows about is virtual. Okay, so notice var x has a virtual address of 4050, just like main had a virtual of 240. Well, all we're doing here is we're loading a constant into A0, and it turns out that constant happens to be an address 4050, but we're just loading the address 4050 into A0.
Okay, so
But we're not doing anything with the address yet, so we don't have to go to DRAM to load that address into memory. Now, this is why I go through this example, and I apologize that this, animation screwed up. Basically, when I converted this to 2010, it did this to me, and I didn't notice it caused the problem. But you with me on this? Good. Another question on this piece. What else is confusing to everybody? So all the addresses that the processor deals with are virtual addresses, and the only time we ever translate is when we're going to DRAM. Okay? So the only time we translated was right here. When we go to fetch 240 hex, we actually have to go to DRAM. So we divide up the physical segment as 0. The offset's 240. Okay, the way we know that is there's 2 bits of 0 up here. The rest is 240. Then at that point, we look it up in the table and we say, oh, look, that base, because we're virtual segment 0, the base is 4,000. The limit's 800. Since the base is 4,000 and the offset's 240, we add those together, and that gives us 4240. That's a physical DRAM address, which we're now going to look up. Yes?
so basically, virtual addresses are only translated to physical on load and store. That's it.
You could say they're only translated on loads and stores or instruction fetches if you call that a load. Okay? 'Cause, I'm being a little bit semantic there, but load and store are instruction types, and instruction fetch is a kind of load, but yeah.
So if you wanted to get the actual value of that variable, you have to translate it.
Yeah, notice all this is in LA, this is load address. When we actually try to use it, we're going to have to go through the translation process. But for now, A0 actually has the value 4050 in it. Okay? Let's see if we go a little further. So the next thing we're going to do is jump and link, JAL, to string length. Okay, that's down here. So that means we're going to jump to the address 360 virtual. Okay, so notice we going to fetch this instruction first, 244. Translate it to 4244. Hopefully we won't have to go that to again, just like we translated to 4240. We pull this instruction out. We now know that when we return, we're going to move 248 into the return address. Why is that? Because we're jumping and linking here, but when we return, we're going to return after the jump and link. Okay? And then we're going to move 360 into the PC. Why is that? Because we're jumping to 360. Notice that in this particular instruction, again, all the stuff relative to the processor is virtual. The one time we translated was when we had to go to memory to find this jump and link instruction. Okay? Question? Now let's take a look at what's going to happen next. Okay, so all we've done is we've loaded an address in here, we've done a procedure call to here. Now we're going to do something interesting. Well, we're going to load immediate a 0 into V0, so that's kind of boring. So in fact, all that we're going to do is probably very similar to what we did before, right? We're going to fetch the instruction at 360, which means we translate by looking up to exactly as we did before, and we end up with 4360 as our virtual address. We pull out this instruction that moves a 0 into V0, and we add 4 to the PC. Okay? Now, everybody with me? Now we're going to get something interesting, right? Because now what we want to do is we want to load the data that's at the contents of A0 into T0. So LB stands for what? Load byte. All right, so somebody explain to me what's going to happen here to make that work. So we're going to try to execute instruction at 364. First thing we have to do is what? Go ahead, what? So we have to fetch the instruction. So the first thing is going to look exactly like before, right? This is kind of boring. To fetch at 364, we translate to 4364, we get it. Okay? Now, notice that address A0 is 4050 virtual. So now in order to load the byte, now we're going to DRAM, we're going to have to translate. Okay, somebody tell me what is the segment ID for 4050? Okay, I hear 1. How many people believe it's 1? Okay, it is 1. So those of you who don't think it is 1, let me help you. How do you know it's 1? Yeah.
4 is binary 0, 0, 1, or 0, 1, 0, 0, whatever instruction you're going.
Yeah. So if you guys don't know how to translate between hex and binary, you should do that soon. Okay? No, I actually am saying that not in jest. I mean, it's easy to not be able to do this quickly in your head, but it's useful. So 4 is 0, 1, 0, 0. Okay, which means the top 2 bits there are 0, 1, which means we're segment ID 0, 1. So let me put the table back up here. So notice that here, segment ID 1 has a base of 4800. So notice that to translate 4050, we notice we have virtual segment 1, and now the offset is 50. Why is that? Why is the offset 50? I know this seems like simple, but I want to make sure we get it. Go ahead.
All the lower bits.
Yeah, basically, if we mask off the 0, 1 at the beginning, everything else is 0, 0, 0, 0, 50, right? Okay? So if this is the base, 4800, and the offset is 50, then our load address is going to be 4850, where we load a byte from 4850, and we're good to go. All right, so there was an actual translation situation. It's kind of painful, so it's a good thing hardware is usually involved. Okay? Are there things that don't make sense to people on this? Are we good to go? Any other questions? So you could easily do this if it were to come up on an exam or something, right? Okay? All right, yes, question?
There's no differentiating between when you switch segments. Like,
Yeah, so this particular scheme, so you're saying that going from the bottom of one segment to the next segment doesn't have anything obvious to differentiate. Well, that's true. The only time that would ever be valid is if the previous segment were the full size, right? It would have to have a limit of 0x whatever 3ff, or basically, yeah, that's right. But other than that, no, it's no difference, right? Good question. Okay, actually, the limit would be 4,000. Actually, is what I meant to say. Okay. Okay. So midterm 1 next Monday. Okay, I've gotten some email from 1 or 2 of you who can't make the exam time. If there's anybody else, make sure to send me mail. I suspect that we'll have the makeup exam on Tuesday. So I'll say that. It's otherwise it's 6 to 9 in 155 Gwinnell. I'm going to swear, by the way, the people who might have to take it the next day to not talking to any of their friends. We know. Closed book. 1 page. You can write on both sides. You can write as small as you can read. Okay. I know that people sometimes want to print things out using really fine fonts and their printers, but let's say handwritten. Okay, so handwritten, 1 page, both sides. Don't bring 3 pages. Okay, you shouldn't need a calculator or anything either. No class on day of midterm. I'll have some extra office hours from 2 to 5, I'm pretty sure, next Monday. The other TAs will offer some extra office hours. Midterm topics, everything up to this Wednesday. Okay? Make sure to fill out group evals if you haven't. And people who are having problems filling out group evals, is that all resolved? There are some people who didn't get email back, but you should check. It might be the email that you signed up for it when you used the register program. I'm not entirely sure.
So if you did it on Friday and you emailed back and got signed,
You hopefully got emails back. If you didn't, you should verify with somebody that things got registered. Yes?
I'm pretty sure it's getting sent to the IMAIL account associated with it. So if you're CS162- whatever.
Oh, okay, so it's getting sent to your CS162-whatever account.
Yeah, so you would log into IMAIL.
Okay, so you're going to need to log into IMAIL, I guess. Okay, thank you for that piece of information. I'm sorry that it's at a weird place, but we didn't write those scripts. So, Project 2, initial design docs due on Friday. So I realize things are tight, but we're on this Tuesday to Friday to Tuesday schedule with 3 weeks total. So getting up close. And then next week, we're going to try to schedule the design reviews too. So it's going to be a tight week. But hopefully that'll work out. Any other questions on Administrivia? I think that's good. Okay. Good. Project 2, by the way, hopefully will be a little less challenging than projects 1 and 3. That's the rumor. All right. Good. So let's continue for a little bit here. So some observations about segmentation. So the first thing to note is that virtual address space has holes, right? We saw the holes. And so that basically says that segmentation gives you a way of making a sparse address space, which is sort of a useful thing. Maybe you want to have the stack in one part and the heap in another, and you want them to grow toward each other. So this is a scheme that gives you that possibility. And although a correct program should never actually try to write in the gaps, maybe that's useful because you get a segmentation fault and you go ahead and fill out the segment. So if you take a look here, just to remind you of the gaps again, see the gaps? This is a gap, that's a gap, that's a gap, that's a gap. We've got those gaps exactly because of the way we're dividing the bits off here. Okay, that's our gaps in our address space. Okay. Boy. Weird animation problems there. Okay. So when it's okay to be out of the valid, when is it okay to be in the gap? Well, we haven't talked a lot about this, but one of the reasons to be in a gap is exactly like we said, to grow the stack and the heap. And that's exactly the way systems work. You assume for a moment that it's only going to need 4K of stack, and then if it uses a little more, they get a page fault or a segmentation fault, and you get 8K and so on. And the stack will grow automatically because of those faults. We'll talk more about that as we go further. You need protection in the segmentation table. Okay, so for instance, we could easily label segments as read-only or whatever. Data and stack might be read-write. The instruction might be read-only. Shared segments, which I'll show you in a second, could be read-only or read-write, so that's kind of nice. What do we save and restore on a context switch? The segment table. Okay, that little green thing I showed you is exactly what describes the state of a process. Okay, and in many cases that segment table's in the CPU, so you'd save and restore it in the CPU. Okay? In that weird complex scheme with the x86 I mentioned, there's the segment table in the CPU, which are the 6 segments, but then there's also the segment tables in memory, which you don't have to save. Okay, those would get referenced as you swapped out the segment table or the segments descriptors. Okay. So let's now ask ourselves, can we have more memory use than memory? Okay, and clearly the answer is yes. And how would we do that? Well, one idea here is this notion of swapping. Okay, and what is swapping? Swapping is an extreme form of context switch in which you take all the memory from the process, you toss it to the disk. Okay, so notice I'm swapping out process 1 and swapping in process 2. It's literally I'm copying all the memory out to disk and then pulling all the memory for process 2 back in. And as a result, I have more flexibility in my memory management. So I can actually have a process that's not running. It doesn't have to be taking space in memory anymore. It can actually be out on the disk. Okay? Now, this is kind of expensive, as you might imagine, right? If I've got if I've got 2 gigabytes worth of data, it means I got to write 2 gigabytes out to the disk just to swap in something else. Okay, so we're going to have to fix that in a little bit. But does everybody understand conceptually that with swapping, now suddenly we have as much memory space to deal with for processes as the disk size, which could be a terabyte or 2 terabytes or whatever your disk is these days. Okay, rumored to be 2.5 or 3 by the end of the year. So per single drive. So what's an alternative? Well, swapping seems like a good start, but it seems rather expensive. Wouldn't it be nice if we could put parts of a process out to memory? Okay, and unfortunately, as you might think about it, the segment view that we've given you doesn't let you do more than swap a whole segment out at a time. Right? At best, the hardware we've talked about, let me just go back to it here for a second. There it is. Nope. There we go. Good. Oh, almost. Too far back. Here we go. At best, this kind of hardware support really only lets us swap out whole chunks, whole segments at a time. In which case, we swap a whole segment out. We could mark this as N. And then if they go to try to access that segment and we get a segmentation fault, at that point, we could swap that segment back in from disk. Okay, but this hardware does not give us the flexibility to have part of a segment in disk. Okay, it just doesn't. So what do we have to do? What do we need to do? Split something up. We need segments to be finer. We need to chop the segments up. Okay, and hopefully by chopping up the segments, we also gain ourselves some protection against fragmentation. Okay, so paging is going to be our fix for fragmentation. Okay, so what is a page? A page is dividing memory. We're going to divide memory into fixed chunks called pages, and as a result, we're going to use the fixed chunks to handle everything. Okay, so the problem with segmentation, as we mentioned here, is you got variable-sized chunks, and you got to fit them into memory somehow. Okay, and basically, you've either got to swap out or move processes multiple times to fill the holes in to deal with the variable-sized chunks. And so fundamentally, fragmentation here is a problem with the variable-sized chunks. And by the way, we'll take this moment to talk about 2 types of fragmentation, both internal and external fragmentation. So external fragmentation is basically the gaps between allocated chunks, okay, because if you think of the chunks, it's external to the chunks. Internal fragmentation is basically fragmentation within chunks. So once you've allocated a segment, now perhaps not all the memory in the segment is being used by somebody. Okay, so what we're going to try to do is we're going to try to address the external fragmentation by making all the pages the same size. Okay? So we're going to allocate physical memory in page size. And once we do that, once we pick everything to be the same size, then we can just have a simple allocation vector of bits to say which pages are in use or not. 1 bit per page. Okay, so in principle, if you've got 4K pages, you've got 4 gigabytes of DRAM, then you've got 1 million pages to deal with, and so you'd need 1 million bits. Okay? Now, should the pages be as big as our segments? No. We want segments to be bigger than pages, because we want pages to be the unit that we use here. Is everybody with me on that? Okay. Questions? Yeah.
With 64-bit addresses, you could imagine them bit maps getting very, very large.
Yes, you could.
To the point that they won't fit in a CPU anymore. So what do you do?
Well, the bitmaps could get very large. I will point out, however, that if you think of fitting in the CPU, meaning that it fits in DRAM, then DRAM itself, the DRAM size grows as the amount of DRAM, and the bit vector grows with that. And so there's always enough space to hold the bit vector. It's a question of whether you want to waste all that space with the bit vector or not that's in DRAM.
Okay, but would DRAM then double the access time request or the time required for this request?
Let's hold off access time for a moment. We're still talking about techniques here. We'll get to access time next lecture. Okay. Everybody with me so far? So now we're going to try to deal with page sizes, okay? So what's a page size? Anybody know what a typical size of a page is? Yeah. 4K. What else? 16K. Okay. 32K. Those are getting a little rarer. 1 megabyte. Well, those exist. Okay, we'll show you why you might have really big pages another time. So how do we implement paging? So here we go. Here's a new scheme where we have a single page table pointer register, okay, and a given process has its page table pointer register pointing at a page table in memory. What's a page table? A page table is something with a page number, which is a physical page number, and some access bits like valid, read, write, etc. Okay? How do we do translation? Well, this particular type of translation now is a little bit different from the segment translation in the way that we use the offset. The offset's much easier here. So the offset represents the size of a page. So for instance, if this is 10 bits, we have 1K pages. If it's 12 bits, we have 4K pages. Okay? So this is the actual offset within a page. So to do our translation, we literally copy the offset. We're not going to add the offset to a base like we did before. And the only thing left to go from virtual to physical is to figure out what to fill into this little dotted segment. And how do we do that? We take the virtual page number here. We use that as an offset in our page table. That gives us the page number, which we copy into our physical address, and we're done. Okay? Now, if this is 4K pages, how many virtual page numbers are there? Suppose a 32-bit address space. Good question. 4K pages means the offset is how many bits? 12. 32 minus 12 is 20. 2 to the 20th is? Order of magnitude. Quick.
2 million.
No, 1 million. Okay. So there are basically about a million, a little more than a million, pages in a scheme with 32 bits and a 12-bit offset. Everybody with me? So potentially this is 20 bits, which we use to look up an offset. And what does that mean about this physical page number? Well, if the physical address space is also 32 bits, how big is the physical page number? How many bits? $12. No. How many? 20. Why? 12 bits here, just like there was 12 bits there. If this is 32 bits, then what's left is 20. Okay? I realize that I'm doing these little computations, but you'd be surprised in an exam, for instance, how subtracting 32 minus 12 gets you all sorts of numbers that aren't 20. Okay? Now, there are some things about this scheme that are missing. Like, for instance, we might want to know how big our table size is. Right here is an example with only 6 entries. So our page table size is 6. And therefore, if we actually try to go too high, then we'll get a fault. Okay, what that fault says is we're accessing an address that's too big for our page table. Okay? The other type of error we have to check is if you're trying to do, say, a write in this situation, and this thing is only marked as valid and read-only, we should get an access error. Okay? Now, why are we not checking the offset to see whether it's too big or not? Okay, because it's identical in both physical and virtual address. Okay, what does that mean? Okay, that's right. Yes, go for it.
You can't have an offset that's outside of your page because otherwise if you create it with 10 bits, you get the next page.
Okay, yeah, you guys are all kind of orbiting around this. All of our pages are the same size, right? And the offset going from 0 to 1111 in binary is the set of offsets in a page, right? So that part, I mean, this offset part is not checked because it doesn't need to be. So that says that basically in this paging scheme, we're only allocating chunks of memory in the size of a page. There's no notion of allocating half a page here. Question, yes? Well, that's a good question. Why would this access error ever happen? Well, if you tried to use an address that was too big. Well, it could mean, in this case, that there's something wrong with your user program. Well, we can't, if I understand your question here, you're saying, shouldn't there always be as many page table entries as there are bits here? Well, that would say that every virtual address space has a translation for all 4 gig of addresses, regardless of, let's say, in a 32-bit address space, regardless of whether we're using all that memory or not. So the answer is no, because we want to get back to allowing us to have gaps in the address space when we want, so we can do things like grow stack space and so on. There's a couple of ways to look at what you'd like to do here. So one is we could build a page table that was 1 million entries, because there's 20 bits here, with most of the things set to n. Okay, right? We could do that, and that's kind of what you're implying. That would cause us to get access errors over here. But if we know that the address space isn't that big, then we're basically wasting a bunch of storage here just for pages that are never going to be valid. And therefore, we might as well just set the page table size, and then we could grow the page table size if we needed to add more entries. We could. So you're saying if we swap them, so this is an example of a page that might be swapped out. But beyond the end of it may actually be a part of the address space we're not using. So think of it as we could either get the access error here or here, and that gives us more flexibility in the operating system as to what we allocate. Okay, because 1 million entries, each of which might be 4 bytes wide, okay, because there's certainly 20 bits there, would mean that basically you're using 4 megabytes just for page table entries you're not using much of. Right? So that's expensive. Yes?
In this model, is your page table size, like in this example, would it be 6?
Yes. Page table size is 6, and therefore, this should be greater than or equal, I guess, depending on how you want to compare it. But okay, good. Any other questions? Yeah.
So is the virtual page number the first? Say the page sizes are 4K. Does that mean the virtual page number is the first 20 bits?
Yeah. Virtual page number, the high 20 bits.
So what happens to the stack then? Because the stack is usually from the very top, right?
So okay, so good. So you guys are all thinking ahead. So question here is, where's the stack? Okay, now in order to do the stack in the way that we were talking, we are forced to go to 1 million entries here, which was suggested earlier, with most of these set to no. Okay, and if we did that, then we have the ability to translate the whole address space where there's a few valid pages at the top and a few valid pages at the bottom. Okay? Well, it makes page tables big. Okay, and we're thinking 32 bits. Start thinking 64 bits. Okay, that's really big. Okay, so one of the fundamental problems, which have just been pointed out here with this scheme, is this doesn't deal with a sparse address space very well. Okay, or you remember how our segment scheme we had earlier had these big holes in it? That actually could be viewed as useful in some circumstances, whereas here we've sort of gone back to requiring continuous page table in order to handle this simple scheme. So we're going to go to a multi-level page table in just a moment. Good question, though. Yes? Could you have an array that's so big it spans multiple pages? Sure. And the cool thing about this scheme is the CPU is working in virtual addresses like we saw with our example, so it doesn't even have to know that it's spanning pages. The hardware is just doing this translation on the fly automatically. So if you have an array that's 2 pages in size, you start counting from 0, and you get up to the first page, and then when you cross that boundary, the offset goes to 0 again, and the virtual page becomes 1. And what's happened is you've sort of gone to a different part in DRAM, but that's all hidden from the program. Program never has to know that that array, doesn't have to know that there are pages underneath it all. Good question. Yes?
What is the, I guess, the overhead factor of having pages in memory that are in different places? So where you would have, is there none in this scheme?
So the overhead of having pages in different places is, according to this scheme, none. It's fine. It doesn't matter where they are, right? These pages could be all over the place.
So if your array was half in page 1 and half in page 5, would you have to swap out all the your registers or?
Well, if it's half in page 1 and half in page 5, then as far as the processor is concerned, it's not a continuous array. So that's a little funny already. Right? Because remember, this set of pages represents a continuous address space for the virtual side. The fact that these guys can point anywhere, so you're saying physically page 1, physically page 2. But see, so I would say what happens, I think the scheme you're thinking about is that page 1 points, I don't know, to 0, the 0 part of memory, and page 2 points really high in DRAM. And we have some addresses that cross over here in an array. Processor never knows the difference, and according to this scheme, there's no cost to that. Okay? Now, where costs may come into play is when you start talking about caching and other things like that, but we won't worry about that for now. Good question. Any other questions? All right, let's take our brief break, and then we'll come back and we'll continue. All right. Let us finish up. So I just want to make something completely clear. There was a good question in the break. These physical page numbers that I've got here don't have to be contiguous in DRAM at all. They could be widely varying. What we get is we get a contiguous address space as far as virtual memory is concerned, could be paged all over the place. Okay? Is everybody with me on that? These page IDs don't actually have to be consecutive at all. Okay. That's kind of the power of paging. Let's talk about sharing. Okay, we'll deal with the fragmentation problem that was brought up a little bit in a moment. But how do we share data here? Well, two processes can share data very simply. Here's process A's virtual address space and process A's table pointer. And we can have a certain range of the virtual address space point to some page. And for process B, we can do the same thing with a different page. They can point to the same physical page. And as a result, process A can access at this point in its address space, and process B can access at this point in the address space, and they get the same page. All right? So in fact, and notice what I did here. I was clever, so to speak. Notice how this entry, is marked read write, and this entry is marked read. So because of the way I've set this up, process A can write this page, process B can only read it. All right? Now notice also that this physical page doesn't go to the same part of the physical or the virtual address space for the two processes. So process A accesses it at one point in the virtual address space, process B at a completely different point in the address space. So this is an example of a type of mapping where if you say communicated a pointer from process A to process B, the pointer wouldn't work because the virtual addresses are different. Okay, so if you really wanted to pass pointers back and forth, you'd have to make sure that there was page 2 here that was mapped to that shared page. All right, is everybody with me on that? Now, so what needs to be switched on a context switch here? Just the table pointer and the limit. Okay, that's kind of cool, right? Because the page tables are in memory, so you switch two registers, and as a result, you're suddenly got a new address space. So that is our little switch routine, where before we were just switching out the registers for a thread. Now if we were going from one process to another, we just have to switch these two registers. We've got a whole different address space. Okay? So what about this simple page table technique? Pros of this are it's very simple. It's easy to share. Cons are, well, this sparse address space issue, which was brought up a couple of times. Okay? For instance, if you have a 32-bit address space, you might want to have code down near 0 and the stack near the top, and suddenly you've got 1 to 4 million page table entries that you need. Okay? So this is assuming 1K pages, you'd have 4 million page table entries. That's a lot. Okay? So that's bad. What if the table's really big? So, 64-bit address space, not all the pages used all the time. It'd be nice if you could page the page table. Okay, so, all right, is everybody with me? So we're talking about dividing things up into pages so that we could put pages on the disk. How can we do that, by the way? Look at this scheme. If we decide, what about page 4? Well, it could be that page 4 is just off on the disk. And so when this process goes and tries to access page 4, what happens is a page fault happens. The operating system goes and pulls this page off the disk, marks it as valid, returns to the process. The process goes and tries the access again, and it works. Okay, so we've actually allowed with this paging scheme to now put page-sized things on the disk rather than whole segments. But if this page table gets big enough, wouldn't it be nice if we could put parts of the page table on the disk as well? Okay. The answer is that would be nice. Well, let's take another stab. What if we try to combine paging and segmentation? Okay. Now we're going to need some sort of multi-level translation. So here we go. Let's build a tree of tables. All right, so the lowest level page table is still going to allocate memory in chunks called pages, so there'll be a bitmap. Higher levels can be segmented. Okay, and we could have any number of levels, but we're going to do this with just 2. So now we're going to take the address, and we're going to divide it into 2 chunks up here. So say we have a 12-bit offset. We're going to take the remaining 20 bits, and we're going to divide them into 2 chunks here, rather than having 20 bits at a time. And of course, just like before, we'll copy the page offset to the physical, so that's fine. So the trick is going to be turning these 20 red bits into 20 red bits over here, okay, going from virtual to physical. And so we're going to dump a page table in here, but now the base, a segment table, excuse me, but now the base and limit are about base and limit for a page table, not for memory. So here we go. We take our virtual segment ID, we look up a base. That base points at a page table. This limit is now how many page table entries? Okay, so now we take our virtual page and we use that as an offset into the page table we got from here. So we look up the base. Now we do a virtual offset into this page. That gives us our physical page number. Okay, so we're going through 2 levels of translation. And of course, where can we catch errors? Well, for one thing, if this virtual page ID is bigger than the limit, that means we're trying to go beyond the end of this page table, will cause a fault. Or if we're trying to access something that's invalid, we'll also get an access error. And then the last thing is we want to check the permissions, and we could get an access error there too if we try to do a write on a read-only page. Okay. What do we have to save and restore in the context switch? Well, here in this scheme, it's going to be this green thing, because the green thing is kind of the part that's unique to a process here. Okay. Questions? Notice how we're back to having segments that can be anywhere in our address space, which is kind of cool. Why can they be anywhere in the address space? Well, because basically we've got holes like we did before. Okay, so if you remember that original segmentation thing, we had holes. That allowed us to make our address space sparse, so some of these segments could be for stack, and some of them could be code, and so on. Okay? And then within a segment, we use paging to allow us to page parts of the segment in and out. So we're no longer required to send a whole segment to disk. We can put part of a segment to disk. Okay, is that getting complicated enough for everybody? Could we do, yeah, go ahead, question. So the reason we only have to change the green thing on a context switch is these guys are in memory somewhere. And so, basically, all we're moving is the pointers to each of the segments. And we can leave these sitting in memory. So think of them as maybe in physical memory, if you like. So we can put them anywhere in DRAM we want. Different processes will have their own segment or their own page tables in different parts of memory. And so the only thing we have to change that's unique is kind of the green piece. Okay. So what about sharing? Can we share here? Yeah. So for instance, we can share a whole segment. Okay? So notice how this virtual segment can point at the beginning of a page table, and this virtual segment can point at the beginning of a page table, and so we can share a whole segment, or we could share individual pages. All right, you get the point, right? Just a question of when we map to the same physical page number. Okay? Here is a very common 2-level page table. So let's ignore segments again for a moment. And let's go and hit head-on this question of, well, the page table that I showed you to start with didn't really handle sparseness very well, because in order to get a full address space, we'd have to have all the entries from 0 on up to 1 meg or whatever. 2 levels helps us take care of that problem. So here we go. This is a 2-level page table. We start with a page table base pointer, and notice how the first level page table is going to be 1 page in size. So our pages are going to be 4K. I'm going to show you some magic fitting here. Ready? 4K pages. Page table entries are 4 bytes. So how many of them page table entries fit in a 4K page? How many? 1K, right? 1024? What's 4K over 4? 1K. All right? How many bits is 1K? How many? 10. So, here's a virtual address. Offset 12 bits says we have 4K pages. We're going to have 10 bits at the first level and 10 bits at the second level. Why 10 bits? Because that's 1,024 entries. So we take the first index, we look up a particular entry, that points us to another entry. We take the second index, that points us to another entry. And when we're done, we have our physical page number. All right, what's magic about this is 10 plus 10 plus 12 is 32. Okay, believe it or not, this particular scheme works very well on 32-bit processors with 4K pages. Okay? And notice, it looks complicated, but it's not so bad. Let's trace this through again. Process's page table pointer points to a page with 1K entries. We take the first 10 bits, we look up which of these 1K entries, so this is an offset in this, that gives us, well, it gives us 4 bytes, which point to, among other things, another page, which has 1,000 entries, 1,024 entries. So that means this guy looks up a particular entry. And when we're done, we peel off the physical page, and that gives us, in combination with the offset, a description of which page we've got. And the cool thing is, all the levels of the page table, as well as the pages themselves, are all 4K in size. So everything in this system is 4K in size, so we can actually page parts of the page table. Why is that? Well, because, for instance, suppose we wanted to send this part of the page table to disk. All we'd have to do is mark this pointer as invalid, then we could send this to disk. Yes, question? Well, it has to be marked invalid. It has to be actually marked invalid because the hardware is walking this page table. So you need to make sure that if you look that item up, the hardware will fault.
Right. So you have a separate bit that distinguish that, this is this page number as opposed to
Well, in principle, what happens is you mark it as invalid and you use the leftover bits for disk addressing. But you do have to mark it actually invalid in a way the hardware understands. Questions on this? Magic? Okay. Now, what if you've got a 64-bit page table, or 64-bit machine? Well, there's a lot more levels. Okay? Now, let's look at some pros of this is you only need to allocate as many page table entries as you need. So notice, by the way, let's talk about Unix with stuff at the bottom and stuff at the top. What's cool about that is we only have to allocate valid page entries here, and the rest of all of these guys could be invalid, and then we would have stuff at the bottom of the address space and stuff at the top of the address space, and we don't have to waste any page stuff for the middle, okay, just by marking things invalid. So suddenly this scheme works really well for a sparse address space with stuff at the bottom and stuff at the top. Okay, or any combination of sparseness. All right, so that's why this is commonly used. It's very flexible. Okay, it's pretty easy to allocate if you do that sort of page chunk thing that I showed you. It's easy to share, so you can share it sort of page level very easily there. Cons of this are, well, one pointer per page grows pretty rapidly. Okay, another thing is the page tables themselves have to be contiguous, although in that previous example, we've just made sure that the contiguous part is never more than a page in size, so maybe that's good. 2 or more levels of lookup per reference. As you could imagine, we're trying to make memory fast, and suddenly we've got to look up at the beginning, then the next one, then the next one. Eventually, we look up the actual entry. Okay, so I don't know about you, but if I were trying to make hardware fast, something like this would make me nervous, because suddenly the loads and stores are slow. Right? Doesn't that look awful? I mean, you're basically doing DRAM accesses to figure out what page you're in, and maybe that data is in cache somewhere. So that looks bad. So we're going to have to actually introduce something next time called a TLB to cache things and make it fast. Well, this suffers from a little bit of internal fragmentation, but not too much. Okay. Yeah, although it's a lot less fragmentation than you might have if you had the full page. Yeah. So let me tell you about another alternative here. So previous examples, the size of the page table is of order the size of your virtual address space. What do I mean by that? Well, if you think about a virtual address space that's mostly used, the amount of page table you need grows as the amount of virtual address space. Okay, and so as a result, if you've got a 64-bit address space, you're using a lot of page table, no matter how sparse it is. And so wouldn't it be nice if we had a page table scheme that grew as the amount of physical DRAM rather than the amount of virtual address space? And the answer is yes, you can build what's called an inverted page table. And you'll get to actually build one of these in Project 3. But the idea here is we're translating from a virtual page number to a physical just as before. But now, rather than going through that complicated table, what we're doing is we're going through a hash table. And the hash table is translating from virtual page to physical page. And the number of entries in this hash table really only grows kind of as order the amount of physical memory we have rather than the amount of virtual memory, because you can assume that if something isn't in the hash table, then it's not in the page table, and it's a non-mapped address. Okay? Is everybody with me? And there are actually a few machines that have inverted page tables directly in hardware. Okay? Not as many as you might think, but there are. They do exist. Okay. Of course, the cons of this are complexity. All right. So finally, as a last topic here, if we've got all of these page tables, we got to make sure the user can't alter their mappings, because otherwise all of the protection we thought we had is gone. And so we have to restrict somehow, and we've had this discussion before. And the idea is that your hardware has to provide dual modes, kernel, user. Okay, now of course Intel actually gives you 4 levels, okay, which are called privilege levels. From 0 to 3, PL0 is the highest level, PL3 is the least. Okay? And I just wanted to give you a little thought here. This idea of protection is a funny one, because if there's only one CPU, that one CPU is both acting as jailer and jailed, right? It's running code that's either modifying the page tables or being protected by the page tables, and that's a problem. And we got to make sure that the user can't change the page table mappings. Okay? And so, you might ask the question, well, how do you share the CPU between the kernel and the user? Well, you got to make sure that when you're going from user mode to kernel mode, that it's very controlled access. Because if you can do that arbitrarily, then suddenly the user can alter their page table entries, and that's a problem. Okay? And we'll talk about this last time, but I want to point out that going from kernel to user mode should be easy, because that's a lowering of privilege, and that's okay. Okay, so the fact that the kernel, for instance, when creating a new process, might allocate the page tables and read the program off the disk and do all these privilege things, and then at the very end sort of go into user mode and jump to the start of the program, is not really a big deal. Okay, because it's lowering its privilege. What gets a little tricky is the other direction. Okay, and this is, can the inmate get out to manage the store? All right, and we'll pick this up next time. But this notion of a system call, which I've talked about before, is a very restricted voluntary procedure call into the kernel. And the way it's restricted is only certain routines are able to be called from user space to the kernel. Okay, and the way that restriction happens is, while there is a hardware instruction called a trap that lets you go from user to kernel, that trap has an explicit ID encoded in it, and only those specific starting points that are specified in IDs are allowed to be run in the kernel. So it's not like the user can say, put me in kernel mode and run this arbitrary code, which happens to be code I've got. Unless, of course, you're running on a user's Windows system and it's a virus or something. But the way this is supposed to work is very controlled. And so next time, we're going to talk more about this. So let's, in conclusion, memory is a resource that we want to share. We talked about controlled overlap, translation, protection as goals. We talked a bit about dual mode as protecting our actual schemes. Okay, basically making sure the kernel is the only one that can alter the translations and the user is not allowed to. Okay, we'll talk about more of that next time. We showed you what segments can look like. We gave you a simple segmentation scheme. Okay, and I actually walked you through a couple of things. And then we've talked about page tables, which are much more flexible. Key idea there is pages are fixed-size chunks. Okay, and by being fixed-size chunks, we avoid external fragmentation. We showed you multi-level page tables, which is what actually happens, where we take the address and we translate through multiple levels of table. And finally, we showed you the inverted page table. So have a great couple of days. Next time, we will pick up where we left off. Get going on Project 2.